In the last segment, we looked at oxidizers or reducers, or oxidizing agents or reducing agents. Oxidizers are something that cause oxidation. When they cause oxidation, they cause something else to lose electrons, and therefore the oxidizers will gain the electrons. Therefore, you recognize your oxidizer as that which is being reduced. Your reducer is something that causes reduction. It is causing something else to gain an electron. Therefore, your reducer is something that itself is oxidized. In this segment, we're going to change gears and we're going to talk about nuclear chemistry. We've looked at isotopes before. What is an isotope? Something with the same number of protons, different number of neutrons. Okay? So for example, carbon-12, carbon-13, carbon-14 are all isotopes of carbon because all of these have 6 protons. Remember, you look at the periodic table to tell you the number of protons or atomic number, but they have different numbers of neutrons. This one has 6, this one has 7, this one has 8. If you don't remember how to do that, go back and review your earlier notes. Hydrogen 1, hydrogen 2, hydrogen 3 are all isotopes of hydrogen because all of them have 1 proton, thereby making them all hydrogen, but they have different numbers of neutrons. This one has 0, this one has 1, this one has 2. Now, there are what we call stable isotopes, and that is what we have been assuming all along, that the isotopes that we're looking at are quote-unquote stable. They have a stable nucleus. And there are ones that are unstable. The unstable ones are what we call radioactive, and they're generally unstable because of the nucleus. Now, there's different kinds of instability. There are things that can capture a particle, just like a Venus flytrap, okay? Or the nucleus can undergo decay. Here's the nucleus. We're going to give off a particle. For the purposes of this class, we're going to look at nuclear decay, which means that it generally happens because the nucleus is usually having too many neutrons. So for example, carbon-12 is stable, but when we start shoving in more neutrons, that nucleus becomes unstable. Hydrogen-1 is stable, but when we start shoving in more electrons, it becomes unstable. And there is something called a band of stability, the ratio of protons to neutrons. And usually and typically, but not always, the band of stability is 1 proton, 1 neutron. You're reasonably stable, but you start shoving in more than a 1-to-1 ratio, you're going to likely end up with something that's unstable. Nonetheless, when we talk about decay, the particle that is given off occurs when the nucleus falls apart. So we'll have a nucleus, and in its most simplistic terms, we'll have a part of it that quote-unquote decays, and we end up with the new nucleus and the particle that comes off. Kind of looks like breaking an egg, but it's not that simple. Now, how is this useful to us? Radioactive decay involves energy. So remember, E equals hc over lambda equals h nu. So if there's an energy event, there's a wavelength event. Or if there's an energy event, there's a frequency event. Okay? Now, the energy or light can be detected, just like we saw in that atomic emission spectrum lab. We saw those colors. Okay? So because that energy or light can be detected, we can use it as a tracer. We can add a radioactive nucleus onto something and we can trace it because it gives off energy. If it gives off energy, it's going to give off either light or a sound. Because they give off energy, that energy can be used to destroy something that we don't want, and in this case, destroy diseased tissue. Or because they give off energy, they can be used as energy, largely in the form of electricity. Energy is used to drive the processes that give us electricity, and that electricity can be used to heat homes, give us electricity, plug in our refrigerators, things like that. Okay, so they have a strong reputation for being negative, but there's a lot about radioactive isotopes or radionuclides that is useful. Now, many radioisotopes are naturally occurring, which means they are found in the world around us at all times. Okay, now there are three main particles that we're interested in when we talk about radioactive decay. There's the alpha, there's the beta, and there's the gamma. Now these should not be new. If you came from Chem 110, for example, we talked about alpha, beta, and gamma. We're just going to add a little bit more. Okay, now the symbol for alpha is 2, 4, charge of 2, mass of 4. And that should look suspiciously like helium, charge of 2, mass of 4. So you can write your alpha particle as you would a helium nuclide symbol. Beta, charge of -1, mass of 0. 0 mass, charge of -1. And that should sound specifically or suspiciously like an electron. So sometimes you'll see beta decay as written as though it's an electron. Gamma is chargeless and massless. And if we remember at the beginning that chemistry is the study of matter plus its energy changes, matter is anything with mass that occupies volume. So the only thing that would be massless and chargeless is what we would call energy. Okay, now it is a quote-unquote particle, but we're going to think of that in terms of energy. Okay, now because the radioactive decay involves this change of energy, it can damage tissue. Okay, so while it can do good things, it can also be damaging. So if you ever work with radioactive materials, you want to be properly shielded from it. Okay, now the alpha particle, beta particle, gamma particle. In the grand scheme of things, the relative size of the alpha particle is that it is huge. So you can think of the alpha particle, envision somebody throwing a shot put or a bowling ball. Gigantic, huge, heavy particle. In general, how far and how fast can somebody throw a shot put or a bowling ball? Well, most people, most of the time, can't throw it very far. Your relative speed is slow. Its penetration, I'll call depth, it's called penetration depth, very shallow. Okay, can't go very far, can't penetrate paper or wood or metal or even skin. Okay, so the type of shielding that you would need for the alpha emitter, if we're just talking about skin penetration, is really just your skin. As long as you've got skin, your clothing, paper, those kinds of things will shield an alpha emitter as long as you don't inhale it or you don't drink it. Beta emitters are smaller. So instead of throwing the huge shot put or bowling ball, you could envision throwing a baseball. Now, most people realize that some people can throw a baseball pretty fast and pretty far. So we're going to say that this is pretty fast and this is going to go pretty far. Excuse me. So in general, your shielding has to be more robust than either your skin or your clothing or a piece of paper. And most people, most of the time, who are working with beta emitters will be happy to have some plexiglass. Okay? Also, there is distance. Okay? Distance will shield you from alpha emitters, as well. But particularly for beta emitters, because they travel they're smaller, they travel faster and farther, you want something more robust. So plexiglass, so you can actually see what it is that you're working with. Now the gamma particle that we're saying is effectively massless and chargeless is smallest. So now instead of tossing a shot put or bowling ball, or tossing a baseball, you can think of having, say, a BB. And this time, instead of having a BB that you're going to throw, you're going to shoot a BB out of a BB gun. So this is going to go very fast, very far. Excuse me. Okay, so your shielding for your gamma is what you typically think of. Lead, concrete, or sometimes both. So when you talk about, for example, spent uranium that is used for power plants and they're buried in a mountain in casks of lead under concrete inside a mountain, that's what we're talking about here. Now, how is it detected? E equals Hc over lambda equals H nu. When you have a radioactive event or an energy event in the nucleus, you can either see it as a wavelength or you can hear it. So oftentimes with these, you can hear it with something called a Geiger meter. A Geiger meter. And a Geiger meter is the familiar, it's kind of like a metal detector. Tick, 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 tick. That tick sound that you're hearing is telling you that you're picking up radioactive events. There is also something called a film badge. A film badge tends to be worn on the lapel of a lab coat, or you could have a ring badge. Some people wear ring badges if they're working with a lot of radioactivity. And so your nuclear decay is occurring as a flash of light. Flash, 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 flash. And just like in the old days of photographic film before digital cameras, you would get a photographic image of what it was you were trying to take a picture of because you had a flash of light. So a film badge picks up flashes of light and it quote-unquote reads the number of nuclear events based on the flashes that it sees. Over here we have something called a scintillation counter. Okay, and a scintillation counter also detects flashes of light, but it's far more specific and sophisticated than a film badge. Now each of these will have their advantages and disadvantages. Okay, so here come my cats because the dogs are chasing her. So we're going to just ignore her. Okay? Geiger meter has the advantage of being small and portable, but not specific, not particularly specific and or precise. You can pick up some kinds of radioactivity with a Geiger meter, but not other ones. Film badge, small, portable, but again, not particularly specific or precise. Not particularly specific or precise. So you use these to get a general idea. So if you ever work with radioactive materials, you would scan your work area with a Geiger meter and you would go around the room and you would just, have like a metal detector. You would go around and you would hope that you don't get a lot of ticks. Same thing with a film badge. Usually and typically you wear a film badge for a prescribed amount of time. You turn it in, they count it, they give you another one. Okay? These are designed, well, all of these are designed to assess your exposure. The scintillation counter has the advantage of being very specific, very precise, but not portable. And you need a scintillation fluid that allows you to visualize the tick, 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 tick. The fluid is typically toxic. Okay, something that is specifically used for this purpose is going to be likely toxic to our environment. On the next segment, we're going to begin with writing a balanced nuclear equation.